Welcome back. In this lesson, we're going to continue talking about matter and minerals, and we're going to look at what composes minerals. So we're going to do some very basic chemistry. We're going to look at the building blocks of all matter and how that matter comes together and why it stays together. And we're going to look at bonding and some of the various things that will allow minerals to have a very specific shape and very specific chemical arrangement. So we're going to start with a concept, and that is of the smallest particle thought to be one type of stuff. So there's various types of matter in the universe. We've got about 118-ish different types of matter. We call them the elements, and each element is going to have its own unique properties. You can say this has a color or has a density, it has a melting point or whatever, a freezing point. And so we'll look at these various things, and then as we start putting them together, we can start building these molecules that will later be called crystals. So then to begin, all matter is composed of atoms. Whatever that structure that you see, whatever the compound or the substance you're looking at, is made up of small individual parts called atoms. Now, even that is a little bit weird because atom, by its name, means indivisible. It's the smallest thing that's indivisible, but long ago we figured out that atoms are made of themselves of components, that you have protons and electrons and neutrons, and even those protons and neutrons are made of things called quarks. So we're just thinking of them as an atom being the smallest component of a material. And so you can't divide an atom in any physical way, or even a chemical way. An atom is the smallest unit of a substance that you can have. So let's look at these components of atoms then. Protons have a positive charge, and neutrons have no charge at all. Electrons have a negative charge equal to a proton. But an electron is about 1,800 times smaller than a proton. So in terms of mass, an electron is really negligible. So an electron would be, if you were weighing yourself on the bathroom scales and a ladybug walked on your shoe, it's not going to change your weight that you can see. The number is not going to go up, because even though that ladybug is not massless, it still has some mass. It's such a small amount that it would round off anyway. A proton and a neutron have very, very close atomic masses. So the amount of stuff in a proton and the amount of stuff in a neutron is really, really close to being equal. So you're talking about different amount. You're talking about masses, which protons and neutrons roughly share the same mass. And then you're talking about charges, and a neutron, because it's named neutron, like neutral, proton being positive, electron being negative. So you have charged particles and you have masses that we're dealing with. The electron is going to be attracted to the proton that's in the nucleus. The protons and neutrons stay in the nucleus, and the protons are held together by a really strong force, stronger than electricity, stronger than magnets, called the strong force, believe it or not. And they are held in the nucleus, and the electrons orbit around the nucleus. So they don't spin like a train on a train track. They're much more like a cloud, three-dimensional cloud, a certain probability of where you would find that electron in space. And so there's various energy levels that an electron will have at a certain distance from the nucleus. The electrons will start forming in internal shells and external shells, just continuing to build out from the inside out. And then the very last shell of electrons is important. It's called the valence electrons, like a wedding veil is on the outside of your face. So these are the very outermost shell of electrons, whatever that happens to be. So if you have a very large atom with lots and lots of electrons, you would have lots of inside shells, and then you would have an outside shell. If you have a very small atom that only has a few electrons in it, then you would only have a few internal layers of shells and then an outside shell. And in the case of, say, hydrogen or helium, there's only one shell of electrons, and so its only shell is its outside shell, so it would still be called its valence electrons. We're going to see that the valence electrons are what actually does chemistry. Valence electrons are either stolen or shared in an attempt to make that atom more stable. Okay, some further definitions. The number of protons in a nucleus defines that element. So for instance, if you have one proton in an atom, you will have hydrogen. That's the definition of hydrogen. It's based upon the number of protons. If you have more than one proton in the nucleus, say 2, then you no longer have hydrogen, you have helium. That means that the properties of hydrogen go away. There is no more properties of hydrogen. Now you would have properties of helium. It would act like helium. If you sucked it, it would make your voice squeaky. Okay? If you put it in a balloon, the balloon would rise. So the material or the element that you have is actually defined to be based upon the number of protons. Each new element having one more proton than the last in the table. There's about 118 elements that we know of. A couple dozen of those have been made in the lab. So there's about 91, 92, I think, that are naturally occurring. You could dig them out of the ground, or they're in the air or in the water. So that would be naturally occurring. And then other elements where they've monkeyed with the protons and neutrons to try to like a Jenga tower, trying to make a new element, but often that element will only last a millionth of a second or something before it disintegrates, because it's really hard to do something that was never done. All of the elements that are known are put on a table called the periodic table. So a period would be like a first period, second period, third period, where you have a beginning of class, middle of class, end of class, and then the bell rings and you start a new class. That's periodic. And so periodic means that in this table, it's lined up in a way that repeats the similar chemistry. For instance, anything in the first column is going to behave chemically like each other. For instance, if you were to put sodium, which is a metal, it's a consistency of cream cheese. You could cut it with a plastic knife. It's silvery color. If you put it in water, it would blow up. You'd get a little explosion with a little bit of fire. Well, potassium works the same way. If you were to put it in water, it would explode. Rubidium even more ferociously. Cesium, I would get out of the way, okay, because it's going to behave chemically the same as the other. So it's periodic. That's why the periodic table is so useful, because you can use it to make predictions about what will combine with what and what the result will be. Okay, so as we look at all of the minerals that we're going to be studying, they are made up of certain elements that themselves you can know something about. So finally, we're going to look at chemical compounds, which is usually a chemical combination of two or more elements that have a definite composition and a definite properties. So for instance, sulfur is going to be powdery, it's going to be yellow. Copper is metallic, it's going to be shiny, it's going to be hard, it's going to conduct electricity. They're going to have certain times or certain temperatures that they melt or turn into gases. So one thing is different from another based upon what it's made out of and the structure of that substance. So when we look at minerals, we're going to be looking at a chemical compound of two or more elements, and then these native elements, these are all native elements, native elements are same, is the idea that copper sometimes can be a vein of copper. It doesn't have to be a compound of copper with something else. There's lots of compounds of copper, greens and blues, all kinds of really cool colors. There's compounds of gold even. There's gold in some medicines that you can take where you would actually have a compound of gold. But you can also have a native, just a nugget of gold or a vein of gold running through a rock. Sulfur, you can find sulfur powder. It's actually a very loose stone that sulfur is just sulfur. So that's called a native element that's not a compound.